There are a number of other applications of depth-first search. In this course, we'll only consider one of them, one additional application, but the book covers a number of others, including these: one of determining articulation points, bridges, biconnected components of an undirected graph. But here in this course, we will only cover, as an additional application of depth-first search, the problem of decomposing a directed graph into its strongly connected components. Let us remind ourselves what a strongly connected component is. It's a collection of nodes in the graph such that there exists some path, not necessarily a direct path, from every node in that cluster to every other. That cluster is strongly connected. And we can divide the overall graph into strongly connected components. In some cases, the strongly connected component will be a single node. Let's look at an example. We see here a graph with 9 nodes. And we see that from A you can get to B, and from B to C. Even though you can't get directly from A to C, you can get from A to C through B. So you can get to both B and C from A. Likewise, from B you can get to C and then to A. And from C you can get from A and then to B, so you can get from each of them to each other. And so that cluster is strongly connected. You can also get from A to G, but you can't get back from any path through G to A. Likewise, you can get from A to D, but from D you can get to E and on to G, but you can't get back to A. So there's nothing else besides ABC in that cluster. Similarly, you can get from D to E and from E to D, but you can't, even though you can get from them to G, you can't get from G back to D or E from any path. And so D and E are a component, a strongly connected component. F, G, H, and I are also form a strongly connected component. You can see that F, G, and I form a cycle. We've seen them before, and I to H and back form another little cycle. And so you can get, for example, from H to I, and through I to F, and through F to G, and so you can get from H anywhere. So we have, in this example, 3 strongly connected components. They form a graph of the strongly connected components, the component digraph, which you see on the right. So ABC, that component, you can get to DE, but you can't get back to ABC. You can get from DE to FGHI, but you can't get back to DE. You can get from FGHI to nothing, this is the component-directed graph is necessarily acyclic, because if it was cyclic, the connected components would be bigger. I'm going to explain the algorithm for computing the strongly connected components with an example that we see here. This is an original graph on the top that has nodes A, B, C, D, E, F, G, H, and we're going to initially work on them in that order. We're going to be creating a graph that we call the reverse graph. If you have a matrix, a 2D array describing a binary array with that is an array with binary entries describing the edges, the reverse graph has the transpose of that matrix as describing which are edges. So, for example, you see in the original graph there is an edge from F to E, and in the reverse there's one from E to F. Every arrow has been reversed. Note, however, that if you have a strongly connected component in the original graph, you have the very same strongly connected component in the reverse graph. Take the FEH example. You can get from F to E and E to H and H back to F. There's this nice cycle there. And now the cycle is reversed, but you still can get from F to H and H to E and E to F. So if there was a path from everything to everything, then likewise the same thing happens in reverse. We're going to be using this reverse graph in our method for finding strongly connected components, and we're going to be depending on the fact that if we can find the strongly connected components in the reverse graph, they will be the same components as in the original graph. To be concrete in this example, A and D are a strongly connected component. You can get back and forth between them. You can get off to B and G from them as well, but you can't get back to either A or D. Likewise, B and C form a nice little strongly connected component. E, F, and H, we've already seen, form a cycle. And G, you can get to itself, but you can't get to anything else. And so G is a singlet strongly connected component. It has only one node in that strongly connected component. So I repeat here at the top left what those clusters were. What we would like to do to find strongly connected components is we'd like to get the E, F, and H in the original graph taken care of and seen as a cluster without worrying about the fact that there is a C that is connected to it and an A that is connected to it, from which we can go forward, but we can't get back. So what we're going to do is a topo sort. of the original graph. The late finishers will be ones that complete clusters. And so if we can take the late finishers from the topo sort and treat them first, we will be in good shape as long as we don't leak out, for example, from the H to the C or the E to the A. But the reverse graph will exactly prevent that, right? If you could go from E to A, but not back, now in the reverse graph, you can't get from E to A because you've reversed the arrow that was formerly from E to A and now comes from A to E. So let's look at what happens if we topo sort the first original graph. Topological sort, we will start with A. Its entering time will be 1. And we're going to do a depth first search. So we'll go A to B, let's say. That's the first node that it's attached to. So it gets a starting time of 2. And from B to C, that's starting time of 3. You can't get anywhere from C. So C gets closed at time 4. You got backtrack to B. B still has another possibility, namely G. So G is opened at time 5. You can't get anywhere from G, so closed at time 6. You backtrack to B. That gets nowhere else you haven't already been to, so you close at time 7. You backtrack to A, which has another possibility yet that hasn't been looked at, namely D. D gets opened at time 8. It would look at G, but G's already been examined, so we're not going to go there. So we close D at time 9, close A at time 10, and we still have E, F, and H not yet treated. We take the first of those in alphabetical order, E, open it at time 11. We then follow its arc to H, opened at time 12. H could try C, but C's already been indeed closed. So that's not what the method algorithm would do. But it can go to F. F is therefore opened at 13. F's can go to E, but E's already been examined, so F gets closed at time 14, H at time 15, and E at time 16. So remember that we put things in topo sort onto the topo sort list we put them on the right, from the right end to the left, and in order of finishing times. So C had the earliest finishing time of 4, so it got on there at the far end, and G had a finishing time of 6, which meant it got on next. B had a finishing time of 7, then D had a finishing time of 9, and A had a finishing time of 10. And then F was the next finishing time of 14, H of 15, and E of 16. Notice how the topo sort has got the cluster EHF all at the beginning. And the cluster BC is at the end with G between it, but there's nothing that with regard to G, B can go to G and B can go to G and C can't. Well, C can in two steps, from C to B to G. But when we reverse the arrows for the reverse thing, you'll not be able to get from those places to G. So the interposition of G is not going to bother us in finding the BC. Likewise, we have an AD to look at, and we might be worried about B and G, but we will have finished AD as a cycle before we ever worry about B, G, and C. This is the idea that TopoSort is going to allow us to find the cycles as long as we work on the reverse graph to find its cycles, which are the same as the original sort. So let's see how that works. Okay, so what we're going to do is do another depth first search on the reverse graph, but do it in TopoSort order. So we start with E. So E in this second DFS starts at time 1. And so we see in the reverse graph its starting time of 1. And then we go from it to F, which starts at time 2. And then we go to H, which starts at time 3. And then there's nowhere to go. Notice that all the otherwise forward arrows in the original graph are now back arrows, so we can't get out of this cycle. And so we have to close H at time 4, and F at time 5, and E at time 6, and we've completed that little cycle. And we have no arrows from it, so we have to jump to the next thing in TopoSort order. E and H and F have been dealt with. So the next thing in TopoSort order is A. So A starts at time 7. It has an arrow to D, which starts at time 8. You can't get out of D in the reverse graph. So we close D, time 9. And then we look at A. A could look back at E, but E's already been closed. So A is done, and we had 7 to 10. And AD has been found as a nice little cluster that we've closed. So looking back at the TopoSort, the next available node is B, having finished with the A and the D. And we look down, and that's opened at time 11. B goes to C, it opens at time 12. C, only other places to go to H has been closed. So we just close C at time 13 and backtrack to B at time 14. And we're done with this. So each time we jump, we finish off something and have to start a new place, we are starting a new cycle. In this particular case, what hasn't been done in the topo sort, we've dealt with B, but we haven't dealt with G, and so we have to deal with G. G opens at time 15, closes at time 16, and it's done. Notice that the items in the topo sort you enter at some point, and while you're doing the depth first search of the reverse graph, you already checked off some of the ones beyond it. And so when you finish a particular cycle, where you're at is at the next unchecked item in the topo sort list. So we see that this idea of topo sort to produce to close the late finishers in a cluster, to close a cluster based on the fact that it was a late finisher in the DFS of the original graph, allows us to produce an order where these late finishers get done first and never break out because you've reversed the arrows. So to restate our algorithm, we begin with a depth first search on the original graph. We then do a topo sort from that depth first search, if you will, sorting the nodes in their finishing time order from the depth first search. We use that topo sort order to do a second depth first search on the reverse graph. We saw that there were places where we backtrack, and then there's no more backtracking to do. And so then we have to close that and then go on to the next available node in the list. Those places are the breaks in the clusters, the breaks between the strongly connected components. And so we can find them that way. Or if we want to just look at the parenthesizations implied by the starting and finishing times in the reverse graph DFS, we will see that the parenthesizations imply the clusters. That is to say, if something's in a separate parenthesization from another, it's in a separate cluster. At our example, we see that in the reverse graph, there's a parenthesization of H, 3 to 4, within F, which is 2 to 5, within E, which is 1 to 6. And that parenthesization is not part of the parenthesization from 7 to 10, in which A contains D. And neither of those parenthesizations are within the BC that have C's 12, 13 within B's 11, 14. And then G's parenthesized by itself as 15 to 16. Let us say some more about why the algorithm works. The point is that once a first the first depth first search on the original graph starts within a given strong component, it has to visit every vertex within that component before it finishes. In the meanwhile, it may have visited some others that you can get to, but can't get back from. But if we visit the nodes in the reverse graph, in the topological order, each of those depth first searches among the strong components can't leak out into the other components because we blocked them. And so the depth first searches will just stay within the components and never be able to get out, to leak out. Those components either would have been visited earlier in the search, or will not yet have been visited, but there's no arc to them in the reverse graph. So, repeating, the algorithm uses depth first search twice. The first depth first search on the original graph allows you to compute the topological order, and you use that order to do another DFS on the reverse graph. In that final step, the second DFS, each connected component will be complete before going on to other connected components. And thus it will form a separate DFS tree of that cluster before the next one is started. Let's be careful. When I say DFS tree, we have to remove the back edges from the that in the cycles. Let's now treat this matter of the connections among the clusters, between one cluster and another. Let's look, for example, at the EFH cluster, the EFH strongly connected component. It has an arc from E to A that in the reverse was an arc from A to E. And that reverse arc was never traversed in the depth first search. It wasn't a tree edge. It wasn't a darkened edge in the reverse graph DFS, because EF and H were already done by the time you got to A. That break that's implied by not following that edge identifies it as a connector edge between clusters up in the original graph. So in other words, the edge from E to A connects the EFH cluster to the AD cluster. In a similar way, the arc from H to C, when reversed, was not used in the DFS process. It was never followed to identify something that was previously unseen. And so up in the original graph, that arc from H to C is identified also as connecting clusters, and it connects the EFH cluster to the CB cluster. If we look at the arc from A to B, again, when we were doing B to G, we never followed the arc from B to A in the reverse graph. And so this A to B arc is identified as connecting the AD cluster to the BC cluster. There are two more arcs with the same behavior, the one from D to G, which ends up saying we have an AD cluster connected to the singleton G cluster. And the one from B to G says we have a connection between the CB cluster and the G cluster. I'm calling singleton strongly connected components and clusters that mean the same thing. So that when we finish, we have a supernode, EFH, connected to two other supernodes, one with AD and one with CB. And then we have a connection between the AD and BC supernode, a connection with from the AD into the G supernode, and one from the CB to the G supernode. So you can see how the coloring in the reverse graph allowed us to identify which are going to be the connectors among these supernodes formed by the respective strongly connected component clusters. Here's another example of finding connections among the strongly connected components. So in the process of dealing with this graph, we will have found the strongly connected components ABC and DE and FGHI, respectively. But we will also have found that the reverse of the arcs between A to D, A to G, and B to F will have caused restarts in the second depth-first search on the reverse graph. And so those are identified as arcs that connect the clusters. So the first one from A to D connects the ABC cluster to the DE cluster. The one from A to G connects the ABC cluster to the FGHI cluster, and so does the one from B to F connect the ABC cluster to the FGHI cluster. So we see that more than one arc in the original graph can form a single arc between these strongly connected component clusters. Let us now consider the running time for this whole process. The first step was to run the depth-first search on the original graph. And in our previous analysis of DFS, we saw that that took time theta of V plus E. We have to compute the actual reverse graph. We can do that by visiting each vertex and for each outgoing node, reverse it to an incoming node. We will then have visited all the vertices and all the edges once. And so that takes time theta of v plus e. We then need to get our toposort order. We could have done that within the original DFS, but if we do it separately, we're simply sorting the vertices in decreasing order of the finishing time, and we know what the finishing times are, so we can do that with counting sort, which is order the number of vertices. So that's theta of v. We run the new DFS on the reverse graph using that order. That's also going to take theta of v plus e. Each of these DFS trees is a strong component. We output them as groups, means passing through the vertices, theta v time. And then set the connections, which involves looking at which edges have been identified as the not tree edges in the reverse graph. Could also have done that within step 5, but if we do it separately, it'll take time theta of v. And so the total running time is order of v plus e. I've completed the substance of this lecture on how to compute strongly connected components of a directed graph. We now present a worksheet that the students need to answer and turn in by the time of the exercises that will include strongly connected components, which will take place likely on Thursday, the 2nd, I guess, of November. And then a project, an exercise to be done in class in our inverted fashion. You've already done the depth first search of the graph that you see here, and you also did its topo sort. So what we need to do is to do the second DFS, including labeling its edges and starting and finishing times, and produce the connected components and the DAG connecting them.